Hello everyone, welcome to Connecting with Ideas, CWI 101. Let's do some combinatorics. Here we go. We're going to do a little review to start off. So this is combinatorics again. And remember, combinatorics is the fancy math phrase. It's the branch of math which deals with counting. And quick recap. So these first two things are recap. We learned something called the multiplication counting rule. And what did it say? It said that if you have some event, and if that event can occur in a certain number of ways, let's call it M, just to be really generic, in M ways, and then suppose you have another event. So some following event, some subsequent event in ways, and again we're using these variable names to be generic, well then what happens? Then the sequence of events one after the other, that can occur in, and we called it the multiplication counting rule. Why? Because we are multiplying. And so you multiply M times N ways. And that's kind of all there was to that. We then used that. I gave you this example of Fred trying to set up a talent show. And I said, suppose you have, I think there were five performers, and I made these 5 slots, and I filled in, well, there's 5 ways, and then 4 ways, and then 3 ways. Figured out how many ways Fred could order the talent show, and we had this thing called the factorial. And I don't remember exactly how much I talked about the factorial. Maybe I'll talk about it just a bit more. I'll give you a little chart. So the factorial rule says the number of ways that N items, so for Fred's talent show, he had 5 acts, so N was 5. There were 5 acts that he needed to arrange in order is N factorial. And the definition of N factorial is you start with N, whatever it is, so in Fred's case 5, and then you multiply times N minus 1, which would be 4, and then N minus 2, that would be 3, and you go down, and whatever you started with, you keep counting down until finally you get to 2, and then 1, and then you're done. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, and you use a calculator and it says it's 5,040. Or you just memorize it the way I did. I think I told you I took a course in combinatorics as an undergrad, and yeah, we had calculators. Electricity had been invented when I was your age. Surprising. Are you amazed at that? Oh, it was that recent, was it? Thanks. Anyway, there were pocket calculators, but they weren't great. They were expensive. I wouldn't always have one with me. And so I did a lot of these factorials kind of in my head. And that's our recap, because that is right where we left off. Let me show you, because I don't think I gave you a chart of factorial. So I'll just give you a quick chart so you can get a feel for it and put it in your notes. Sometimes having a chart, and what I had in college when I took my combinatorics class, I had a little book, and it had a list of probably the first 20, maybe the first 30 factorials. And why only that many? Because they get really, really big, really fast. So let's have a little look. A table of factorials. And why are they called factorials? In math, things that you multiply are called factors, right? And you might remember, if you've had an algebra class in high school, you had to factor out things. And so factoring, the factors are things you multiply, and factorials are, well, we multiply. So the table would look something like this. We have some n's, and then we have some n factorials. I'm leaving a little space at the top. I want you to leave a little space at the top. We'll come back and fill that in later. Well, 1, and then we're already there, right? We're counting down. 2 would be 2 times 1. And you think, well, that's 2. This isn't hard stuff, Gary. 3 times 2 times 1. And you say that's 6. And 4 times. And you can kind of cheat at this, right? Because you say to yourself, wait a second, 4. And then what are you going to write, Gary? I'm going to write 3 times 2 times 1. Well, you have 3 times 2 times 1, and you know it's 6. So couldn't you just say 4 times 6, and that's 24, and you're done? And yeah, you could. It's really 4 times 3 factorial, because 4 factorial is 4 times 3 times 2 times 1, and 3 times 2 times 1 is 3 factorial. So we could save ourselves some notation there. Anyway, and they go on like that, and I'm not going to do that for every single one because it takes too much writing. I'm not going to go very far. I don't need this much space. I'm only going up to 10. Why? Because those are the only ones I know. This is 40,320. And those I've actually memorized. I just know them because I used them so often. 9, there's too many digits and it's hard and I can't actually do it. And so what did I do? I used the phonetic major system as a mnemonic. And I'll give you a hint. I'll let you think up your own if you, for whatever weird reason, want to memorize what 9 factorial. I look at 3, 6, 2, and I say 3 is an M, and 6 is a sh or a j or a ch, and 2 is an N, and I say 3, 6, 2. Well, there's machine, and then I did something else for the rest. I'll let you make up your own. And then for 10, here again, I kind of cheat because I know if you multiply a number times 10, you just add a 0. And so I just do my machine again and the rest of it. And then I add a 0, and then I put in the commas in the appropriate places. So there's how I've learned those. Do you need to know those? No. You have a calculator. If you need to know 7 factorial, you can do on your calculator 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah, Gary, that takes too long. Well, you might use the table then, or you might look around on your calculator. I guarantee that no matter what brand, what model of calculator you have, unless it's one of those old four bangers, right? We used to call them four bangers. They add, subtract, multiply, divide. And that's all they do. And it has 5 buttons besides the digits. But if you have any reasonable calculator, if you spent more than $10 on your calculator, look around on it and you will see that there's a little exclamation mark. And if you key in a 7 and then you hit the button that has that exclamation mark, it might be an ordinary button. It might be one of those special buttons. So you have a blue key or a green key or a yellow key, and then you push that and then push some other button, which has some other ordinary use, but it has an exclamation mark on it. And if you do the 7 and then the exclamation mark and then hit equals, you'll get 5040, and you'll think, oh, that's way easier than keying in 7 times 6 times 5 times, and just going on and on and on like that. What's the one I left off? It's 0. And what's 0 factorial? You think, well, wait, how can I even count down? I'm already past 1. It turns out that 0 factorial is 1. And there's kind of a tricky reason for that, and we could talk about it later. But there you go, if you want to see what those look like. So if Fred had 10 different acts in his talent show, right? So it's going to be an hour-long show, and each act has 5 or 6 minutes. Well, that sounds about right then, to have 10 acts. How many ways could he arrange them? Millions and millions of ways. These grow very, very fast. There's a thing in artificial intelligence, in machine learning, called combinatoric explosion. And what this means is these factorial values grow very fast. How fast? Well, suppose the talent show were to go over several days, right? And you're going to have 4 nights of amazing talent or a week of talent. And there are 80 different acts, right? Wouldn't you love to go to a rock concert that went for a week and it had 80 different, whatever your favorite style of music is? But think of something like South by Southwest or Tree Fort here in Boise, and how many different acts are there, right? And if you did them all and you put them in order, how many different ways could you do that? And try it on if you have a calculator, and if it does have that factorial button, try it out to see how fast these grow. Put in 80 factorial. Spoiler alert, your calculator can't do it. If you put in 80 factorial, it will say error. And in fact, 80 is not the largest, the smallest number that will happen on. So try it and see where your calculator breaks. Your calculator probably works on 60 factorial. And it won't give you every digit. It'll have E something. It will give you an answer in scientific notation. New stuff then. Yeah, combinatoric explosion is an issue because if you think to yourself, well, Google Maps is going to tell me how to get from point A to point B. I'm going from my house to the Boise Town Square. I'm going to the shopping mall to buy something, right? How many different ways could you go? And you think, well, at every corner, you could say, well, here I could turn left, or I could go straight, or I could turn right. And whatever you do after another block, you're at another location, and you could turn left, or you could go straight, or turn right. And then after a block, you can turn left, and it goes on and on and on like that. And you think, whoa, that's a lot of decisions. And when you use the multiplication counting rule, you multiply these together, they get big really, really fast. That's why you need either very, very fast computers or very, very intelligent algorithms, computer programs. Okay, so we have this thing called a permutation, and I'll define that in a second. Here comes the permutation rule. The permutation rule says the number of permutations, and I'll underline that so you know it's a vocab word. What is a permutation? It's an ordered arrangement. And you think, oh, we already know this, Gary. We just learned if Fred wants to arrange 5 acts in a certain order, then how many ways are there to do it? You use that factorial rule. You say 5 factorial, and you use your calculator, or you multiply it by hand, or you look at the table, and you say it's 120 different ways. We did that 2 weeks ago. So we already know how to do permutations. And we do know how to do permutations if there are 5 acts and all 5 acts are going on. This is a different rule because we're not going to use all n. We do have n items, but we're only going to take r of those. So we call this n items taken r at a time is, and we write it this funny way. Remember, I've talked about mathematical notation as typically being the result of some sort of laziness. Mathematicians don't want to write 7 times 6 times 5 times 4 times 3 times 2 times 1. And so they invent a notation, the exclamation mark, and they say this is called a factorial. If you see 7 exclamation mark, then you pronounce it 7 factorial, and it means 7 times 6 times 5 times 4, and it's easier to write 7 exclamation mark. And so something like this, it's an easier thing than writing permutations of n items taken r at a time. And it's got a little tiny n and it's got a little tiny r. And here's the formula for it. You do n factorial in the numerator, the top of your fraction, and n minus r factorial in the denominator of your fraction. And that's the rule. I don't know if I should mention it now or later. Your calculator probably, again, if it has an exclamation mark button, what would be the exception? Maybe an online. So if you're using the Windows calculator, I'm going to open my Windows calculator here. Yep, it has n factorial. There's the button right there. It's right above the 9. So it's built into that. If you have an Apple or an Android phone or tablet or device, whatever it is, if it has a built-in calculator, I know it has the factorial. It may or may not have this. But if you have a real live, a handheld calculator, a Casio or a Texas Instruments, any of those will have an NPR button, and it might be hidden away somewhere, right? And so if you have a user manual and you think, oh, what? Yeah, who has user manuals anymore? I can remember when I got my first calculator, it had a user manual, and I read through it carefully to figure out all its features. Now, the typical way that students find out features, a lot of students just ask me. I tell them stuff, and they say, Mr. Thomas, can you show me how to do that on my calculator? And that would be great, except I'm not there in your kitchen with you watching this. Assuming you don't have the owner manual handy, what you can always do, and I'm giving this as an extra tip, key in whatever your calculator says. So if you have one of those cheap $12 things, it says TI 30X-2S, right? Say, that's one model that a lot of students have. It's one we recommend. Or it says TI 83 or TI 89 or whatever it is. Casio, I don't know the model numbers of the Casios. Key that into Google and then key in either the word permutations or just key in NPR, kind of like the radio station. You might get extra weird hits from that. But if you do that, your very first hit will be a little 2-minute video in YouTube that you can click on, and it will show you how to find the NPR button. And actually any feature that you think, gosh, I wish I knew how to do that, Does my calculator do whatever it is? Key in the name of your calculator and key in what you're trying to do, and you'll be surprised it probably does. And someone explains it to you. So that's a good tip to know. Alrighty, I want to see an example of this, Gary, because I don't understand this yet. So here's our example. Fred has 6 candy bars. They're from Halloween, right? He broke open the bag. He bought it, told his wife, honey, we have to have this because the kids are coming in a week. She said, kids aren't coming. They're going to cancel it because of COVID. He says, yeah, but what if they don't? We have to have candy. Okay. And then he starts eating it, right? What does he do? He decides that his waistline being what it is, he can't eat all 6, but he decides to eat 4 of them. Like that's going to make a difference. Honey, I'm not breaking my diet. It's not like I ate all 6 candy bars. I only ate 4 candy bars. They're small. They're bite size. They're fun size. I'm just having fun, honey. How many different orderings are possible, right? He could eat the Baby Ruth first, and then the Reese's Pieces second, and the Snickers third, and the Almond Joy fourth. How many different orderings are possible? Or he could, choose some other ordering, and he might choose a different 4 candies. And I'm underlining orderings. I'll tell you why in just a second. The reason I underline orderings is that when we are counting things, sometimes order matters. And to Fred, when he's eating his candy bars, order matters. He doesn't like to eat 2 things with nuts in a row because, they both have nuts. He wants the variety. He wants the silky smooth. So, and then he doesn't want to eat M&Ms and then eat peanut M&Ms because, they're both M&Ms. So if order matters to you, then you are doing a permutation. And in a few minutes, we will have a different thing, and it will be when order doesn't matter, and it'll have a slightly different formula. But for now, we're doing permutations of n items, 6 candy bars, taken 4 at a time. So that's our formula. You say 6p4. And that's how a math person would say it. They would say 6p4. Actually, before we do that, let's do it the old way. Let's use the multiplication counting rule. I'm going to change colors just because I'm writing up here. This is the multiplication counting rule. And you'll see, we don't need no stinking formula. How many candy bars is he eating? He's eating 4. And so this is a typical way to set up any sort of counting problem is you create slots for each of the things, each of your events, and then you ask yourself, well, how many ways can Fred choose the first candy bar? And you say, well, aren't there 6 candy bars? Yeah, well, then I guess there's 6 candy bars he could choose. And then how many candy bars are left? Well, only 5. And how many candy bars now? He's eaten 2 of them, so there are only 4. And then there are only 3 left, and he's stopping now because he's only eating 4 candy bars. And this looks like it's 360 ways. So that would be one way you could do it. And why wouldn't you do it that way every time? Well, look how much stuff I had to write. I had to write out a bunch of stuff. And if this number were big, suppose there were 12 candy bars and he were going to eat 8 of them, then we've got 8 slots and we write 12 times 11 times 10 times 9 times 6 times 5. Yeah, that doesn't sound like fun to me. So there's the multiplication counting rule. You can do it that way, but let's do it with the permutation rule that we just learned. It will look like more writing because I'm going to do it in super slow-mo. All I'm doing here is I'm taking this 6 and I'm putting the 6 there. I'm just copying this formula and I'm filling in my numbers. So it's a fraction. It has a 6 factorial in the numerator. It has a 6 minus 4 factorial in the denominator. And if we subtract 4 from 6, you get 2. And I want to caution you, just in case you do this by hand, sometimes students think, oh, 6 divided by 2, that's 3, so it's 3 factorial. Nope, factorials don't work like that. And it goes back to if you ever learned the PEMDAS rules. This factorial is really a grouping symbol. So it's in the P's, it's in the P category, just like parentheses are. You have to do the 6 factorial first. and then you have to do the 2 factorial, and then you can do the divide. So that's the thing. Don't try to do 6 divided by 2 first, because you'll get the wrong answer. And then you say, well, 6 divided by 2, I know what that is. I have that little chart. It's 720. And 2 factorial, I know what that is. It's 2 times 1. And hey, it's 360 ways. I'm having a deja vu feeling. I like it when you can do a problem 2 different ways and get the same answer, right? Both times. That's good stuff. It's very reassuring in any case. So there's an example of the permutation rule. And how would I do it if I had to do a lot of these? I would not do it like this. Oh, I might, because it's kind of fun. It's kind of relaxing. If the numbers aren't too big, you can do them. It's not a struggle. Even without a calculator, I used to do them. But nowadays, if I had to do, 6 or 8 of these, if I were in a math class, and we do have math classes that teach this permutation rule, right? All of this combinatoric stuff comes in Math 123, Math in Modern Society. It also comes in Math 153, Statistical Reasoning. You don't get it if you take algebra or trig or calculus, which is kind of too bad. It's not difficult. That's why they put it in those other classes. They think, well, let's give these kids something easier. They're weaker in math. Yeah, I think it's kind of more interesting. But if you had one of those classes and you had to do a page of these, and yeah, there would be a chapter where you have to do a page of these, then I would use my calculator and I would find the button. There is a button called NPR, and how would you find it? Key into Google the name of your calculator with the word permutation or NPR. And then you know how to do it, and you hit the 6, and then you hit the NPR button, which might take 2 or 3 keystrokes. And then you hit the 4, and then you hit equals, and it says 360, and Bob's your uncle, you're done. So that's kind of nice. What's our next Combinatorics rule? Well, it is the combination rule. That's what it's called. And what will be the difference between the combination rule and the permutation rule? The difference will be that with the combination rule, order doesn't matter. Combination rule. The number of ways to choose a combination. And choose is an important word here. You'll see this in a lot of the problems, even in the symbol. And what's a combination? That's an unordered arrangement. I'm not even going to call it an arrangement. I'm going to call it an unordered, because they're not arranged in any way. It's like there's 4 of them. Of n items, taken r at a time, is, and it's combination. And so the letter here, instead of being a P for permutation, is a C for combination. And a lot of people, especially, I was going to say especially older people, but I don't think that's even true. I bet it's almost everybody. I tend not to do it just because I don't know, because I don't. But a lot of people will pronounce this as N choose R, right? I emphasize this word choose up here. And they say C is choose. You're choosing R items. You're choosing 4 items out of 6. And how many ways can you choose 4 of them? And well, what order? It doesn't matter the order. You're grabbing them a handful at a time. So here comes the formula. And again, if you Google your calculator model with NCR, there is probably a button that does this, because this has a little more work. It starts off looking just like what we had, doesn't it? You're thinking, hey, Gary, you're making a mistake. This is the permutation formula. And this is the permutation formula. And the problem is permutations is orderings. So I have orderings. I don't care about the order. And so if I've chosen, say, 4 items, so I have 6 items, I'm going to call them A, B, C, D, E, F. They're letters of the alphabet. There are 6 letters of the alphabet. Choose 4 of them. And you say, well, okay, how about A, B, C, D? Well, great. Now, how do you count those? If you're doing permutations, then you say A, B, C, D. That's one ordering. A, B, D, C. Well, that's a different ordering. So now I have 2. How about C, A, D, B? That's a 3rd ordering. And D, B, C, A, that's a 4th ordering. And you could go on and on and on. And how many different orderings are there of 4 items? Well, there's 4 factorial. What happens if we are just choosing 4 items? So here are your 6 letters, A, B, C, D, E, F. Please choose 4 of them. And you say, how about A, B, C, D? And I say, nice choice. And you say, how about A, B, DC? And I say, that's the same 4. That's the same choice. That's the same combination. And you say, well, how about DCBA? And I say, no, no, that's the same combination too. And you say, how about? And I say, no, no, no. If you count all of those, you will be 4 factorial times too many. And so that's what we do here to finish this formula is we divide by 4, in this case, factorial, R factorial. Cool. Let's do an example. It's Fred again. Fred has 6 candy bars. He has them in a little bowl, and he's heading out for work. He didn't have time to make a lunch because, Fred oversleeps. So he doesn't have time for lunch. He doesn't have time for breakfast, is what I should say. And, breakfast, the most important meal of the day. I suppose they say that. So he grabs 4 of them as he rushes out the door. So what's the order that he grabs them? Well, there is no order. He's reaching out his hand, and then he's putting it in the bowl, and he's grabbing a handful, 4 candy bars, and then he's going. And it's not like, well, actually, he picked up the Reese's first, and then he picked up the 3 Musketeers, and then he picked up the Hershey's. No, he didn't do that. He just grabbed 4 of them. There was no ordering. So combinatorics questions always start with how many ways is this possible? And I think I'll switch colors just to emphasize what I'm saying here. Please notice that order does not matter. So if you had to work some problems in combinatorics, the first question you always ask is, it's a combinatorics question because you see this word, how many ways? And if you see how many ways, you say, oh, this is a combinatorics problem. And then the second question you ask is, does order matter? If it does, it's a permutation. You use the other formula. And if order does not matter, then it's a combination, and you use this combination formula. So supposing we don't have a really, really nice calculator, maybe we live a few decades ago, I'm just setting this up. It doesn't take any brains to do this. I'm just copying the numbers into their appropriate spots. And then 6 factorial, well, I look on my little table or I use a factorial button. I shouldn't have written that yet. I want to do it super slow-mo so you can see every single step. I'm going to just write 6 factorial. All I'm doing is this parenthesis thing. So 6 factorial divided by 6 minus 4, that's 2 factorial and 4 factorial. So 6 factorial is 720, and 2 factorial is just 2, and 4 factorial is just 24, and we get 15 different ways. So you might try that. This isn't a killer problem. You think 15, well, that's less than half a page. And you might try it out with the letters. I suggested that A, B, C, D, E, F. That would give you 6 things to choose from, and write down just 4 of them. And so you think, well, A, B, C, D, A, B, C, E, A, B, C, F. Okay, so there's 3. And then how about A, B, D, E, and A, B, D, F, and see if you can get 15 different ways. If you keep them in alphabetical order, it's a little easier to compare them. If I start saying, how about D, B, F, C, and you think, wait, what? Order doesn't matter. Order doesn't matter at all. There's one more rule that's for a different kind of permutation. This is the duplicate rule. Because you can imagine if the bowl has 6 candy bars, yeah, but 3 of them are Baby Ruth candy bars. Well, how do you tell one little Baby Ruth candy bar from another Baby Ruth candy bar? I can't tell, and so if you grabbed 2 of those or 3 of them, anyway. Okay, the number of ways to order, right? So this is a permutation. N items. You're thinking, I know it. It's n factorial. Yep, that's the factorial permutation rule. But in this case, we have some duplicates, and I need some more letters. I've used M and I've used N. I don't want to use O because it looks like a 0. And so the next letter would be P, or maybe Q, or maybe R, or maybe, and I don't know how many different things I have that are duplicates. Where this many of them are duplicates is, and here's our formula, n factorial, that's what you start with, and then you realize, wait, but I've overcounted some, right? So P factorial, Q factorial, R factorial, and then I don't know how many I have. It goes on like that, maybe S and T, and U and V. So here comes an example. Fred has this annoying hobby. He's writing out permutations of his old girlfriend's names. And I've told Fred, don't be doing this. Your wife is going to see it and she'll think, why are you thinking of Lisa? Right? Guys, don't be doing this. Don't be a Fred. So how many ways can he order the letters in, let's use Lisa. And you could try it, right? You could say to yourself, well, how about Lisa, L-I-S-A, obviously, and then how about Alice, and how about Isla? Hey, that's even a word in Spanish. How about sail? Ooh, that's a word in English. They don't have to be words. Ulcia, Asil, I don't know. And how many are there? Well, order matters. Order matters. So, must be 4 factorial. There's 24 ways. And you might try that just to see if you could do it. Okay, let's do a totally different example. How many for Barbara? So Fred has this old girlfriend named Barbara. Her friends call her Babs. No, I don't know what her friends call her. I never met her. Plus, I just made all of this up. There isn't even a person, Fred. My old mentor, John Erdman, at Portland State, for all of his math examples, if he needed a person, he would always use Fred. And then if he needed another person, he would always use George. And the reason is, right, if you've taken an algebra class, you know about functions, and they always talk about f of x. And so f, that's for Fred. And then g of x, well, that would be George. And he used to do that, and I don't think he had any personality for Fred, but over the years I've developed this personality for Fred, and I say that George is Fred's brother, and anyway, I always use Fred for my examples. How many for Barbara? Yeah, that's what I'd like to know. So here comes Fred, and he starts writing them out, and he says, well, just like with Lisa, you could write the word itself. That's one way to arrange them. Barbara. There you go. And then Fred thinks, okay, let me switch some of the letters around. How about bar, ba, ra? And I say, Fred, wait, Fred, what? Stop, Fred. Those are both the same. And he says, no. You said, how many different ways can I order them? I said, yes. And you wrote 2 things exactly the same. He says, no, these are different. Because you see this B right there? That's the very first letter. And see this B right there? It's the 4th letter. Well, I switched them. Yep. See, this B that was the first, now it's the 4th. And this B, I say, Fred, come on. They're identical. No one can tell that Barbara is different from Barbara. He says, well, what, you can't tell the B's are changed? No, nobody can tell the B's are changed. He says, well, I didn't just change the B's, I changed the A's too. See, there's 3 different A's, and this one now it's over here, and this one's over. Fred, no, you can't be doing that. So what happened? Fred, if he does it this way, and he says, well, I switched the B's. Well, how many different ways can you arrange in order these B's? Because that's what Fred thinks he's doing. You say, well, there's 2 B's, and so I guess 2 factorial. There'd be 2 ways you could arrange them, and here's one way, these B's, and here's another way he switched them. And how many ways can you arrange the A's? And he says, well, you would say, because you know the math, well, there are 3 A's, and so there must be 6 ways you could arrange these 3 A's. And if you wrote them that way, what, you could put little numbers, right? You could say A1, A2, A3, A3, A1, A2, and there'd be 6 different ways. But we don't want to do that because these A's aren't numbered. They are, what are we doing? Duplicates. And so if you do what Fred's doing, you will overcount, right? He's got twice as many words as he should have because he thinks he switched the B's. And what's 3 factorial for the A's? 3 factorial, 3 times 2 times 1, it's 6. There are 6 times as many words listed in Fred's silly list because he's thinking that he's switching the A's and also he's switching the R's. And so the way we would figure this out is we would write it. We would say there are 7 letters. There are what? 2 B's. 2 B's or not 2 B's? No, that's not the question. There are 3 A's, and then there are some R's, or 2 R's. And so using this formula, we have n factorial over p factorial, q factorial, r factorial. That's 7 letters in total. And what duplicates do we have? We have 2 duplicates, and we have 3 duplicates, and we have 2 more duplicates. And so 7 factorial. This, by the way, there's no button calculator that does it automatically. You would have to write it out. And again, don't try to reduce the fraction until after you've done the factorials. 3 factorial is 6, 2 factorial is 2. And so we divide, I think, if I've done it right, 210 different ways. That's a lot of ways to write Barbara. I mean, it's worse if Fred tries to do it and says, I'm switching the B's. You'd have 5,000 some names. I mean, this would be pages and pages and pages of writing. It would waste a lot of ink. I think it's a waste. I mean, when Fred's wife sees him doing this, she's going to say, why are you thinking of Barbara? What's the deal? And he shouldn't be doing this. But those are our 5 combinatorics rules. Recap, why do we want these combinatorics rules? Because when we are doing classical probability, our theoretical probability model that we learned about several weeks ago in a video, we need to say the number of ways that something can happen divided by the number of ways anything can happen, and often the number of ways. That's a combinatorics question. So maybe an example, how many cards are there in a deck of cards? You say 52. Well, how many orderings, right? Shuffle the cards. How many orderings are there? How many permutations of 52 cards? And you say, well, 52 factorial, and that's a ginormous number. It's a crazy big number. You might Google for it. There's a nice video about you climb, what do? You take one step every second and you walk around the entire Earth at the equator, and then after you've done that, you take one drop of water from the Pacific Ocean, and then you walk another, and finally when the Pacific Ocean is empty. And anyway, and you do this, and how long does it take? It takes forever. I mean, it takes longer than the universe has been around. That's how many different shufflings of 52 cards there are. It's a huge, huge number. And you might say, yeah, but I'm not doing all 52. I'm just dealing out 5 cards. Oh, a 5 card, maybe you're playing poker. So 5 card poker, how many ways can you choose 5 cards out of 52 cards? And you say, does the order matter? And you say, no, it's 5 cards. And so, okay, use a combination formula, and 52 factorial over 52 minus 5 factorial times 5 factorial. Anyway, you could figure out there's still a lot of poker hands. But that's the sort of reason, that's why we're learning this combinatorics, is so that we can apply it to other probability questions.